Are there any life scientists in the room, or are we all data experts? Life scientist? Or, okay, very cool. Perfect. So I'm going to be discussing GRAKN.AI today. The way we focus, we put ourselves across is as the database for AI. So the reason for that is AI systems process knowledge that's just too complex for current databases. You all know that, you're all in the room. I don't really need to explain the history of databases. But as you know, I started with record keeping in the 60s, 70s. Business intelligence was making a movement. Actually, I think American Express were one of the companies that led that. We ended up with the relational database that took away an awful lot of the complexity that at the time we were having to handle. You can say thanks to Steve Jobs, we ended up with computers in our home, and we needed a new way to be handling data again. We needed web scale databases. And you had the new wave again that could take care of that scale, but we've hit that wall again of complexity, where if you want to be building something smart on top of your database, there is somewhat a limitation of the database. Again, I'm talking to the people in this room, you're all aware of the problems. So what we've set out to do is what relational did for business intelligence is what GRAKN will do for artificial intelligence. So how do we set about looking at this? Actually, 2.5 years ago is when we started, and the origin was Heikel, our CEO, worked for a company called Quintic, where he did a lot of algorithm optimization, including building the systems for the likes of Russian railway network, an Australian coal factory, and all of their supply chain, and his colleagues have worked on things like the DHL supply chain. So one thing they found was every time they finished, they had to start again. They couldn't reuse anything they'd ever built before, and they'd had to start again. And they kind of said, what's the problems we're facing? So one, that current databases don't allow you to model the complexity that actually exists in the real world. Quite often you're limited to binary or kind of an add-on on top of binary, and that's just not how the real world exists. Because of how you've had to model it, your then structure required to query becomes so complex. Your Sparkle queries get longer and longer and longer to cover every single potential outlier and combination just to make sure you don't miss anything. And that takes time, and then you have to let it run, which takes time. So your business and your operations get slower and slower. And then we've also seen how big data is a huge buzzword, but how many engineers can really write those algorithms and actually apply them? And then once they've written and applied them, you have to do it again once you apply it to a new set of data because they're not transferable. So database query languages are too low level, and things had to change. So what we are is a hyper-relational database. This allows knowledge inference, knowledge analytics, and we've actually built right from the storage level. So what does that mean? It's a hyper-expressive schema. You're actually able to model the world as you see it, including inheritance, including multiple different types of relationships. And because of that, because we've worked on how the data is stored, we've been then able to build our own query language on top of that, which means that a query in Sparkle that might have been 300 lines, in GRAKN is 3 lines. And I've got a demonstration that will show you that later. And then because of those two factors, we're able to wrap the analytics in the query language. So all of these big data analytics that people are looking to do, if you've structured your data properly, you're actually able to do that straight through our query language. So because we've kind of taken that higher level of abstraction, the capabilities are much greater. So what I'm going to be using as the example today is BioGRAKN, which was applying GRAKN in the biomedical space. My background is actually biochemistry at Imperial here in London, and this was one of the reasons I actually joined GRAKN. There's so much complexity to the space of life sciences, and there's ever-increasing data, but it's very siloed, it's very separate, and a way to combine it all and be able to query straight away would just be an absolute game changer. So very, very quickly, the central dogma. Francis Crick, 1958, posited this. 1962, won the Nobel Prize for this and much more. In replication, you've got DNA to DNA. In transcription, you've got DNA to RNA. In translation, you've got RNA to proteins. So as a human being, you can infer they're kind of, well, therefore DNA interacts with proteins. And we all know that. So how can we actually use that and understand that? The problem you then face in the life sciences space, and if any of you have had friends that have studied this at university, they can tell you, so much of this incredibly valuable data is siloed in these individual databases. And it's out there, it's available, it's free. As an undergraduate, you can do all of this during your coursework. And I know for a fact a lot of major pharmaceutical companies use these very databases. They have their own private ones they want to add, but actually the core free available ones are being utilized, but they're two separate. But we all know that data, while valuable, you want to get information from, and it's the knowledge that then you're really trying to garner. So this is GRAKN and GRAKL. So you can see on the left, looks very much like a graph, but that's for visualization. This is all you need to define your schema. You've got entities, you've got relationships, and you've got attributes. Any new entity can be a subtype of the previous entity. Therefore, if you have, let's say, employees, you've got part-time, full-time, consultants, maybe different locations. If you want to pull all of them, you can simply say match employees, because they are all subtypes. So that takes you back to what I'm saying of how running a query in our language is much more straightforward because of how you structured that data. And then, as you can see, we've actually pulled the relationship out, if you will. So again, although your people within the graphical space may see nodes and edges, in a sense, you've got an edge coming from an edge because the relationship is separate from the line. So you then have hierarchy inheritance, as I said. So startup may be a subtype of a company. So if you wanted to find startups, you could query for that. If you want to find companies, and that just includes startups, you can do that. So the BioGRAKN schema, the entity and relationships you can see here. Dozens of entities, all these relations from multiple different sources, stored in multiple different formats, across different websites. You understand the complexity. So I was going to do screenshots, but I'm actually able to do a live demonstration, which I think is always much better. So once you've added all of this, can people see that? Let's make that a little bit bigger. No. So what we're looking for here across all of the data once it's been migrated into your GRAKN database is we're looking for a cancer, and this is the language, this is as straightforward it is. A cancer that has the name breast cancer. Now we know that that cancer is related to a stem loop, so it should be on a new line. That stem loop is related to a mature RNA, that mature RNA is related to a gene, that gene is related to a drug, and we just want to find one. So when we run that, this is what we get. Now that's great, that's perfect, but you could argue we didn't need to do all that work, in fact, because with inference, you can simply say, I'm looking for a cancer that's breast cancer, and I'm looking for a drug that interacts with it. And at runtime, our inference engine can find you that connection. Now that data does not actually exist within the data set. That is across multiple different data sets, but what we're able to do is infer those connections just as you could when we said DNA interacts with protein pathways. But you want to know why that's occurred, because a black box is not always that helpful. You can find out. So you can actually pull this out and see where all of these connections have come from. If I actually just refresh that and run it again. You'll see inferred relationship there on the top right. So it's not actually in the data set. So once you've done that, you can actually get a little bit smarter as well and use it for different ways. So we just want to find a cancer that's got reference treatment. Okay, so we know these two, but let's find out why. So when we expand, again, it's a little bit messy today, we can see all these connections, and we can see that this gene is connected by this mature RNA, and that relationship has 4 points of reference that are giving it validation. So it's like, interesting, let's find out what they are. You can actually attach the articles that are giving that weight, which means as the researcher, you just want to know the connection. But once you have that connection, you can really boil down and see where it's come from. All of this is being done at runtime, connecting all these multiple different databases because of the schema. Once the schema is built, the query language allows it to be this much more powerful. So you can now understand, therefore, that your database can do that inference for you. It can take care of that for you, which means that it can think in the same way you think, which is exactly the reason we're talking about ourselves as the database for AI, because you're able to write these shorter queries much quicker, and your database can handle that complexity for you. You're able to push the complexity back down to the database layer. So, I know it's late in the day, and there's an interest in alcohol. So what's next? We are an open source platform. We actually, because of that, have had multiple different pharmaceutical companies download us, install us on site, and start playing with it, and then reach out to us for how we can help. So right now we are doing a project scope with an AIM-listed UK life science company. We've also got one of the major US life science companies building this. This is an incredibly frequent issue for most pharmaceutical companies. But as you can see, the potential that's being applied here works across multiple different domains in multiple different ways. And what's really valuable we've seen with different clients is once you've built this, you can build whatever you want on top. So do you want an enterprise knowledge graph? Actually, this takes care of that. Do you want your business analyst to be able to understand your data and query it? Because of the simplicity of the query language, how quickly it can run, they can do that. Are you looking to then build a chatbot later that uses the same data that you've already stored? Well, because of the structure, because of the simplicity of the query language, you can build a chatbot on top. It can have context. It can handle that. So by focusing on getting that structure and that schema right, everything else kind of can be taken care of later. So that is GRAKN.AI. Happy to take questions. Thank you.